Nie, może być słyszeć.
So let's start. I think we have waited a while. I would like to welcome Fluence Labs, Anna and Bernard today for today's meetup. And I now pass the floor to Anna and Bernard.
Hey, good morning, everybody. Good evening, wherever you are. Thanks for having me. Very much appreciated. And let me just post the link real quick before I'm going to be gone. And let's get going with the presentation. All right, so the topic of today's talk is programming with distributed systems with Aquamarine. And I know this is not the title you were promised, but believe me, it's a very worthy bait and switch. So I hope you will not be disappointed. Before we go into Aquamarine and the way to program distributed systems, especially peer-to-peer systems, let me just tell you a little bit about Fluence Labs. Fluence Labs builds open source peer-to-peer networks, development tools and components to really support developers to master and be successful at programming peer-to-peer and distributed applications. While over the last few years, we've had a lot of advances at the lower level, at the network level, and lower primitive level programming tooling like libp2p. But if you've ever tried to do it on top of peer-to-peer protocols, you know it's still extremely frustrating and very, very challenging. And that's really where Fluence comes in with our ecosystem almost to support developers, to make it easier, to accelerate the build out, and really make it a much more enjoyable experience to build on peer-to-peer. And that's why we actually created Aquamarine. And Aquamarine is a runtime and programming language. Actually, it's 2 programming languages. We'll get to that. That really enables peer-to-peer coordination and composition for distributed applications and backends. Before we actually, as we go on, one of the reasons why we are focused on peer-to-peer is peer-to-peer is pretty much the only way to avoid censorship, and that comes from centralized systems. And this is not just from a political perspective; it's increasingly from a business perspective. As you probably all have heard, multiple companies have been shut down by the likes of Amazon, Facebook, and others, and that's a real threat to an enterprise and to individual developers and app developers. And peer-to-peer offers an alternative to it without too much penalties, and that's a huge step forward, and as part of the entire Web3 movement. So, the need for distributed programming tools. There, as I said, so there is the centralization aspect of it, or the decentralization aspect of it, but at the same time, there's also a use case to be made that allows peer-to-peer programs to run on much thinner, much lighter, much cheaper devices in hosting environments than your traditional client servers. And one of the reasons is that if you look at the traditional request-response pairing processed by client-server applications, let's just say you want to get a Stripe authorization, and then you want to send an SMS to the user to inform him of the authorization process outcome. And so usually what you do is you send your request to Stripe, you get a response, then you turn around and send the response to, I don't know, Twilio, and they send the SMS, and you're all good to go. So in many respects, your client, your application handles an end-to-end request response calls. That's expensive, not just from a traffic perspective, but from the resources required to host or run that application. Peer-to-peer networks allow you to approach this a little bit differently and much more effectively. And basically what it allows you to do is it allows you to take the response from a service, let's just call it S-1, and then to immediately drive that response into the next service S. And so you don't get these intermittent round trips. You just get one forward chain data package delivery that hops from service to service to service. However, while this is possible with distributed and peer-to-peer networks, this isn't an inherent capability. You actually have to work to get this. And this is where Aquamarine comes in and really shines. So what is Aquamarine? Aquamarine is actually, it's an umbrella. Aquamarine is comprised of multiple tools, and one of them is a virtual machine. It's developed in Rust, and it's a WebAssembly module. It is comprised of a low-level language, AIR, Aquamarine Intermediate Representation, which we will be looking at today. And that low-level language is actually intended to be a compilation target, but that's the first one we had. And our our high-level language, which is super ergonomic, you'll really love it. But as I'm advertising it, it's not quite ready. It just wasn't ready today. It's going to be another week or so, and so we'll be looking at AIR throughout this presentation. And what Aquamarine, what that ecosystem allows you to do is, it really enables you to separate the orchestration from the service business logic. And that's a huge step towards getting these efficiencies possible through peer-to-peer networks. It obviously allows you to do peer-to-peer applications. And another aspect that's inherent, it's a first-class citizen within the Fluence Aquamarine vision, is that it allows you to build zero-trust applications right out of the box. For those of you, I'm just going to go very quickly. Zero trust applications, or zero trust, is basically trust nobody. It's an approach. It's a security approach to networks that's really gathering and getting momentum. And you trust nobody, nothing. Everything needs to be authenticated. Everything needs to be authorized. There is no inherent trust in anything. And that's a really an increasingly popular and necessary framework as we start breaking down walls of our infrastructures and get more and more interconnected and collaborative. And this is inherent in the Aquamarine design. And we'll get to that with an example. And so at the bottom, it basically just shows you how it all fits together. Now, in order to get all this done, you need a solid foundation. If you develop a system like Aquamarine, you got to have a solid foundation. And our solid foundation is inspired by PyCalculus. PyCalculus is, if you want to take anything away from this, it basically gives you the mathematical tools to describe and model concurrent systems with dynamic type topologies. And this is crucial. Everything else is wonderful, and it allows us to model and verify and actually build a system and instructions and operators. But it's that being able to model dynamic topologies is huge. And the reason for that is the following. In peer-to-peer networks or many distributed networks, peers come and go. It's expected behavior, not exception behavior. And that makes it very tricky and difficult to model. Because, as I said, like a route you were able to execute 1 second ago may just not be available to you anymore. So this gives you a formal framework to deal with those kind of shifting and evolving networks. So how do you, actually, let me just go back. So PyCalculus comes with a few operators, and if you ever been exposed to, say, lambda calculus, for example, you know that a handful of operators in those formal languages and algebras are extremely powerful and basically let you do just about anything you need to do. So how do you go from the theory then to the implementation? Well, we have a few instructions as well, derived from the PyCalculus, and we basically have an execution command. We have sequential parallel processing. We have a fold operation and branching and an identity. So that's not much, but it's extremely powerful and lets you get a lot of work done very quickly. So what does it look like in Air? Air, recall, is it's the low-level language we're looking at. So you look at an instruction set that's basically comprised of an instruction, like the call, the execution, and then data pertinent to the service and the node. So basically what this statement here says, it says call the function put for service DHT at node peer ID, give it the two values, key and value, and I expect a named output called result. And that's it. And we'll go through all this a little bit more in detail, obviously. And but that's extremely powerful notion. So your location, your peer ID obviously is dynamic. Your service ID may be dynamic, and your function is actually fixed in the sense that it corresponds to the public API of the service referenced. And the key values actually are being piped into the instruction set. So then you get your result. That's it. And that actually allows you to do a lot in terms of peer-to-peer programming. However, we need one more construct. In order to go from one peer service to another peer service without ever going back to your client, you need something that knows what's going on. And this is what we call a particle. So particle is a data structure that combines data, the execution sequence, and some metadata. And how this is implemented, we see on the right. So basically, we have this Airscript, just like I showed you before, and we didn't put much in there except for basically traversing nodes. And basically what it says is go from Firefox, your peer client that initiates the application or the choreography of the services, go to node A, go to node B.
I'm sorry to interrupt.
Yeah.
But I don't see the slides.
You,
I believe there should be slides, so maybe screen share doesn't work or something.
oh, damn it.
I just was thinking that they will appear at some point, but they didn't.
Is it there now?
Yeah, but they weren't there from
Okay. All right. So, oh my God, somebody should have said something. All right. So, how do we reset? Okay. So this was the title. This was, let me just go. Okay. So this was the need. So this is where I was trying to explain how the request response difference between the client server and peer-to-peer application. And as you see in the client server, you get this end-to-end, roughly this end-to-end relationship, whereas in peer you get an end-to-one, roughly, relationship. And this is how you take advantage of the peer-to-peer network. This was the slide on Aquamarine, and basically at the bottom you see the diagram how it all relates. This was the slide on PyCalculus, where on the bottom you see those inherent operators, and this was the slide on air. So let's go back to that one. So our instructions are on the left hand, and on the right side in the diagram you see the air instruction set. Again, that expression basically tells you to call the function put for service DHT at location peer ID with the arguments key and value, and we expect the named output result. And this is where I think I got called to order to put the slides up. I'm really sorry about that. And the particle. So again, particles are data structures that combine data, execution sequence, and metadata. And in the implementation example, you see how that can be expressed in air. And in that example, we initiate the sequence by a browser, Firefox Relay, which is a peer client. And then we go from node A to node B to node C. Eventually, we end up at another browser called Chrome. And so these particles travel from service to service. And as it's programmatically specified in the air implementation, and basically resolves along the way. And the Aquamarine virtual machine does a really good job at every peer to make sure the particles travel where they need to travel. So what does that look like from a different perspective? Here, so think of this application, for example, as a chat application, peer-to-peer chat application, right? And we got this big circle, which is our network, which in this case, a Kademlia network. The white squares are the nodes, and the little red dots are the services on a node. And you can have more than one service, obviously, per node. And then depending on your service requirements, you write your Airscript, like, for example, on the right again, which is the same as from the previous slide. And now this particle starts traversing the network according to the programmatic specification you, the developer, has given it to do. And in this case, so we're going from the browser to some services, and then we end up at the Chrome. So for example, I'm sending a message, so we got a message service somewhere, and we want to add emoji, so we got an emoji service somewhere with a file upload right there, and then it goes to the Chrome browser, and now you have hello with a smiley face emoji ending up at the Chrome browser. And this is obviously really, really powerful, and this illustrates how the separation of the workflow, if you will, and the service is extremely powerful, and really brings out all the advantages and capabilities of distributed and peer-to-peer networks. Let me stay on the slide for a second. As I said in the response request, by separating the workflow, you take a huge load off your front-end application, in terms of resources required to host it and to run it. And that actually changes or could change where an application is hosted. So lighter requirements allow us to host applications, particularly with WebAssembly in browsers, on very light mobile devices and on IoT devices, and particularly on the industrial side. Peer-to-peer networking and IoT, I think, has a huge future. It's already taking place. And with peer-to-peer, obviously, you're somewhat transport agnostic, especially with libp2p, and you can very easily switch to Wi-Fi Direct or a variety of mesh networks, which are extremely pertinent to IoT. So again, this is an extremely powerful way to lighten the requirements for your client and take advantage of the capabilities at the node level, which we believe is a huge advantage over traditional programming approaches and network approaches. So where does this get us? So for the purpose of this presentation, so I ended up coding up a couple little services, and let's just go through them. One is called an Echo service, and let's just say it's deployed on Peer A. And basically, we're building in Rust, we're building a small application that then will compile target on WASI. And there is some markup that's Fluence specific in order to get the Rust to WASI and Aquamarine capabilities in place. But fundamentally, what we're doing here is we're taking an input, which is an array of strings, and returning an array of echo structs, which the only member is a string. And obviously, that doesn't really mean much, but I needed an entry into a service, and the entry, rather than building an SQL or MySQLite or whatever service, this is just very quick, and it's a proxy to stand in for any kind of database or other storage-based service you could possibly imagine. And then we have a greeting service. The greeting service basically just takes a name, which is a string, and let's just say the greeting services are deployed on different peers, multiple peers. So how do we actually go from the echo service to the greeting service? And we do this with Aquamarine. So the services are the same, so I just really made them very small. And so now we built an Aquamarine, an Airscript. And basically, so don't be afraid of the parentheses. It's once Aqua comes along, you don't have to deal with it. So one more week maybe. But basically, what we're doing is we're entering. We're calling a public node the relay node, and we're calling the echo service. And in this particular case, our arguments, our values are names, which are piped in. And in our case, if you look to the right, are Bob, Bill, and Jack. So what can we do now? So we now specify a workflow that calls the greeting services by decomposing the result. The named output, echo result, is now the input directly into subsequent services. In order to get a semi-decent size of the diagram of the code on the screen, I only use 2 greeting services. And what we're doing is we're decomposing the echo result manually in this case into 2 arguments for 2 different services, one on node 2, one on node 3. One is greeting service 1, one is greeting service 2. And then at the end, and in each call, we now have a named output, and there are 2 separate ones, a greeter result from the first service and a greeter result from the second service. And then at the end, we now call and check on our results. And this is what we get. We only use 2 services, and we had Bob, Bill, and Jack going in, and we have Bob and Bill coming out because we only use 2. And if you look at the decomposition, echo result 0, echo result 1 is Bob and Bill, and that's what we got back. So this is how we took advantage in a kind of a lame way with sequential processing and knowing the inputs to quickly get to the workflow into the consuming service and values. However, we can do better. And how we do better is we use fold, we use an iterator. And what we've done here now is we have, we call again the same service, the echo service, and we pipe in Bob, Bill, and Jack. And now we fold right here. And we basically decompose and call our iterator variable item. And then we just go to one node, greeting service 1, and we pipe in the item iteratively, and we get an array of results now, which, as you see, is hi Bob, Bill, and Jack. So that's pretty cool. Didn't have to do anything. And again, the particle traveled from the echo service to the greeting service and iterated over the requirements. Are there any questions at this point? Let me check the chat real quick. Okay. And let me move. Okay. I think Alexei already said in the chat, I just saw it, that how the VM resolves it. And as I said, it's on a per node basis. So now I wanted to show you something different.
Bernard.
Yes. I heard an echo there.
Sorry, there is a question in the chat.
Yeah, if I have the, okay. Well, it's deployed from an application, so so I'll show it to you in a minute. But once it's released in the wild, if you will, it travels according to the path you give it. You programmatically specify it. So the logic to route, the resolution logic is on each of the nodes. So a VM, an Aquamarine VM, is on every node. Is that your question, Wardam?
Got it. Thanks a lot.
Okay. So I wanted to show you one more example, and actually more than that, but an alternative way is you can run services in parallel. Now, this doesn't make much sense for what I've done. I forgot. It just occurred to me very late last night, and I didn't get around to code up another service, so I'm just talking you through it. So basically what we're doing here is we're taking the item and piping it into two services in parallel. So again, for the inputs, Bob, Bill, and Jack, you now get back two arrays, Bob, Bill, and Jack. That doesn't really make much sense, right? But if the greeting service, if I had been enough foresight, I would have not just had the function take a name string, but also a Boolean value that determines whether or not I say hi or bye. And now we could have piped into the second greeting an additional variable, or in both cases, one true, one false, and we would have ended up with hi, Bob, Bill, Jack, and bye, Bob, Bill, Jack. So, and if you look at the length of the program, if the air, it's super efficient, and you can accomplish a lot with relatively little code in this peer-to-peer environment. In part because the Aquamarine components, especially the VM, take care of all the heavy lifting, and that is really the whole point, to make it easier, to make it accessible, and for you to, as a developer, to have fun doing it and actually get results you want. So I'm missing a slide now. Big surprise. Hang on. Okay. So I wanted to show you one more thing. I talked about zero trust and inherent security. And in Aquamarine, services are exposed to actions in form of functions, and they may require authorization. And the easiest concept is what's generally referred to ambient authorization, where authentication gives you authorization. It's basically, it's in Linux or most operating system, that's how it gets, right? You get your user authentication, and that gives you an ambient authorization realm to work within. And that's pretty much what you get out of the box with Aquamarine, even though you can extend this very, very significantly. And the core concept in Aquamarine is that of a tetraploid, which is basically the peer ID, the service ID, the function name, and the data getter. And that allows you to enable secure composition of functions within Air. So now let me switch. Okay. So we probably don't want to see that one. Let me. All right. So I got a Docker container running. That's the actual node here locally. So just so you can get a look, let me close this. We pulled the Docker container for the node, and it starts you up, and it gives you a whole bunch of things right up front. It tells you what the Air interpreter is, which is the Aquamarine virtual machine. It gives you the certificates for the key pairs, and it gives you the unique server peer ID, which is really important because that's, as you saw in the Airscripts, this is what we need to call or refer to when we specify peers and peer location. And then you get your traditional connectivity and your basic libp2p like logging with a lot of Fluence and Aquamarine particulars. Okay, so we get that. And let me see, there should be another one. And I prepared another service. This is probably too small, so let me make it here. So the greeting service we saw before, I re-implemented that, but now I'm putting in a check whether or not the caller is actually the owner of the service. So anybody who's ever done any Solidity programming, for example, you know this, like origin equals owner. And the way we've done that is we inherently take advantage of the security tetraploid that's built in, that comes with Aquamarine, and we do the is-owner check. And from the inherent call parameters, that's where we really start to referring to the security tetraploid, we check whether or not the caller is the initiating peer ID and whether the owner is the service creator peer ID. And then we just do the Boolean check, and that gives us whether or not somebody is the owner of the service. As I said, this is ambient authorization. There is much more we can do, but I think for today, this is pretty much all we need to do. So now going back to the greeter. So if you're not the owner, you get an error, and if you are the owner, you get the error hi, whatever. And instead of just a string, I created a small struct. I call it greeting result or result, and it has two members, public obviously, one's the greeting and the error string. So you have to put a little bit of effort in resolving whether or not this is a good call or a bad call, but it's not particularly difficult. If error string is empty, as you can see, then obviously it goes to result. And that's it. So let's have a look. So, all right, this is probably also way too small. So let's make this bigger. Okay, so I'm using a tool called FLDist, which is a tool, a Fluence tool, command line tool to interact with the node and to build, to deploy services, to do all the kind of heavy lifting. You can also use a JavaScript SDK to build actual applications rather than just command line. But for our purposes, the command line should just do. So what are we doing? This is the CLI application. Now we're giving it, now we're feeding it the node ID, which I just showed you. Hang on, was right here. And the node address, which is basically the ID plus the local address. We want to run an Airscript. And the Airscript is called greetCL Jake for closure. And let me just, I forgot to show you that. Airscripts. This is the script we're calling. So basically what we're doing, so the XOR, the branching is basically, it's an error catch, right? I think you've seen that. If the first branch doesn't execute properly, you get the second branch, and that gives you the actual error message or the last error through the execution loop. And so what we're doing, basically, you don't see any difference than what you've seen before. We call the greeter. With the greeting service, with the greeting function, we give it the name on the node, which we fill in, and then we get back our result. And that was the part I had shown in the presentation in the slides for the other examples. So we had the node, we give it the node address, we give it the command, which is run the Airscript. We give it the location of the Airscript, and I just showed you what it looks like. And now we come the data. Here comes the data. We're piping in the data. And in the Airscript, you saw the reference to the node, which was the node ID, and we pipe it in like this. And then we need the greeter, which is this greeting service, if you recall, which is this. And this I got from when I created the service. So when you create a service, you actually have to take some notes, manually or otherwise, and you have to take a hold of your greeting service. Although the service ID you can retrieve differently from our dashboard, for example, and I'll show you the dashboard in a minute. And then the name we pipe in was just Booyah. And now we run it. Oh, look at that. I am not the owner. I got barred and there is no greeting for us. And the reason for that is that we didn't provide the authorization credentials necessary. And here now we get the additional flag, which is called the client seed or the seed, and you get the token. And that I also got when I created the service, or I could have specified it as I was creating the service. And this is obviously super secret. You should not share this with anybody, particularly if you're using it to guard your service with the authorization. And now let's see if we add that to our data, what happens. All right. I didn't screw up. Okay, I did it late. And now we are authorized and we get the expected greeting. Any questions about this right now? No? All right. So going back, so going through logs, that's not particularly exciting, but here you see how those particles executed, at least at the log level. All right, now back to the presentation. So you saw that basically just like you do in Solidity or any other, or in Substrate, where you check the origin with against some signed message or private key or secret key. You basically very quickly and very easily get to a very robust authorization capability. And as I said, this is built into Aquamarine through what we call a security tetraploid. So it's out of the box, and all you have to do is write this one little function, am I owner, or whatever you want to call it, and just start guarding your functions on a per function level as necessary. And that's really, really powerful. So, and it gets and also necessary. So imagine you running a database, for example. You obviously want this to be guarded, because otherwise everybody is going to start overwriting your data. And because one thing, I don't know if I mentioned this, I mean, one of the big ideas really is that all this is happening in permissionless peer-to-peer networks, right? This isn't private. These are permissionless peer-to-peer networks where peers can join. They can choose what kind of services they want to host. So it's a really, really powerful yet simple way of bringing access security into a permissionless peer-to-peer or otherwise distributed network. And as you can tell, I'm obviously extremely enamored with the notion and the capability, because I think it's super, super cool, and it solves a huge, huge problem in that space at no expense of the developer. Okay, so for a quick recap, so services in these distributed peer-to-peer network environments are basically business logics, and they're totally built on WASM modules, which share nothing. So they're independent, and you compose services from multiple modules, and then Aquamarine through Air and next week or so, Aqua can call the services exposed API and provide the authentication credentials as necessary to protected methods. So, obviously you can't protect exposed methods from going private, right? So you have to use this authentication mechanism, and that allows you to choreograph services into applications independently from the service's business logic concerns. And I sort of showed you that with that one example, the contrived example where we parallel inputted the arrays into two different services and or different use cases of one service. And this was all without ever touching the service. And that's one of the huge powers of peer-to-peer, and Aquamarine really allows you to access that power very, very easily, in my opinion. There's a little bit of a learning curve, obviously, but I don't think it's particularly hard. So from my end, that's pretty much it. But obviously, I'm more than happy to discuss. And let me go back. How are we with questions? Yes. So if you look at, so I'm going to Shubham. Is there a way to trace? Yes. There is a way to trace. And so first of all, you got the logs, right? But then the other way was you can also, quote unquote, get print statements, if you will. So when you see the results being returned, let me go back to this. So here, for example, we called it, we executed it, we get back what the client seed was, we get the client peer ID, which is my client, we get the relay peer ID, which was the node I'm running, right? Here, that's just Docker. Yeah, we had the peer ID here. And then we had the statement in the execution, in not the execution, in the Airscript, to actually return your result here. That's not really necessary. This is only for us to verify what we've done. If you, hang on, we had Airscripts, full parallel. So in the sequential one, which was, I think, the first or second example, this is the Airscript. And I've been calling the return service up here. So we called the echo service. We piped in the data. And then I called for the results, which wasn't necessary. And this is how you can start tracing where things happen and where things go wrong. Now, in addition, if we can have this built in to make it very going on. So I added to the execution command, I added the a debug log, and that shows you everything you ever wanted to know and didn't want to know about what was going on in your particle execution. So it gives you the part of the scripts where it's going on, what's been executed where, the various traces, the processing outcome, the next peer, and on it goes. So this was a very long answer to the question. So yes, you can trace the routing path, and this is how you can start debugging. Unfortunately, I didn't keep any of my bad scripts, so I don't have any error ones right now to show you, but it's definitely there. Okay, elaborate on fault tolerance. So Shuban, did that answer your question? Okay, great. Elaborate on fault tolerance, error handling with scripts with XOR operation. Okay, all right, so let's go back to okay, so by utilizing, I mean, branching is good for a lot of things, but one of the really powerful applications of branching, or in our XOR, is to branch between what we consider a good path and the failure. So anywhere along the path, so, and this is just one module, if it fails, the branching gets triggered and you get the return service for the last error. And so that does two things. First of all, it doesn't just crash. You don't get a panic, right? You basically get a clean exit from your program. And second of all, it literally gives you, I mean, it's the last error. It gives you the last error that caused it, which, quote unquote, from your perspective, is the first error, right? Because it is where it failed. And that gives you a certain degree of fault tolerance, in the sense that A, you don't end up with a panic, and B, you execute up to that point for the error. And that's actually a pretty neat feature, not just from a debugging perspective, but also from an implementation perspective, because in many respects, you don't have to catch your try except all along. You just basically branch it like you almost do sort of in Rust, where it bubbles up as a result. And that's actually a pretty neat feature, because if I shouldn't probably say this, but if Aquamarine was built or Air was built on the Go model, you had to try and accept at every step of the way your programs would be not particularly ergonomic, and you'd end up with a huge number of parentheses, which you already don't want to end up with. Anything? You're welcome, Alexei. Any other questions, discussions? I mean, it was a fairly high level. I mean, it's a Aquamarine solves a complex problem. So you can't just like, okay, here it is, and nicely gift wrapped. However, we're getting there. We're getting there, and maybe it's not necessary for developers to actually understand all the challenges and the problems in order to be able to successful developers in that peer-to-peer medium. However, knowing at least some of it and why we're doing what we're doing is, in my opinion, at this stage, just as important as it is to know how to use it. And as I said on the outset, most of our code is Rust-based, and I think, and Alexei, you can chime in anytime, we are super happy with Rust. It brings a lot of capabilities. It brings ergonomics, which I think you even see in Air, a way of thinking. And the VM, if you look at the code, so it's I think it's the same GitHub. It's github.com github.com Fluence Labs /Fluence or /Aquamarine. You'll see it's a super tight implementation of the interpreter, and the capabilities Rust brings with to compile into WASM targets is just awesome. And anyway, so I think we're super happy with it, and I think it would have been much harder to build the Aquamarine system in, say, C++ or anything else. I don't even know if anything else would have been possible than Rust. So, and I think over time we're gonna open up our WebAssembly languages, but right now it's all Rust. So if you want to build services, oh yeah. So one thing that's really important is sort of there is an inherent division of labor in these peer-to-peer application and networks, and the division of labor may not be clear, but it's certainly there. And one of the really empowering aspects is that you have nodes that can be operated by hosters or node operators. You have services like the greeting service and the echo service I have on there, except for the one I secured. It's on there. It's on the dashboard. You can just grab it, you can access it, and you can use it, and you can compose it right today. And let me just show you the dashboard real quick. There's a lot of services that might take a minute to load. So the separation of concerns is around the node, around services, and of course your applications. And the application literally is I don't want to use the word gluing together, but programmatically composing or coordinating or choreographing services, deployed services into your application. And that's, I mean, that is not just extremely powerful from an execution perspective, but from a reuse perspective, right? So if we look, so there is here's the echo service I put up. It's on the network. So it's our test network. So if you want to use it, you can. It's right there. And to me, this is an extremely powerful. It's extra slow loading today. Of course, it is extra slow, extra powerful. Sorry, extra powerful approach to developing applications. And I want to go back to the presentation one time, since you are a little bit on the quiet side. I actually developed a little fact section myself. So how do I access services such as generic Web 2 endpoints not hosted on the peer-to-peer network? So this is a really good question to myself. Basically, what you need to do, you gotta build proxy services, also known as adapters, that are hosted on the peer-to-peer network. And we have a whole bunch. If you look at the example repo, there's a whole bunch of examples on how to do that. But we're in the process of kickstarting sort of an adapted development sprint in the not so distant future. And open source developers certainly have an opportunity to participate. And I think we actually could put some Gitcoin efforts toward it. And so that's that. Another question. Oh, great. Do I have to run a peer-to-peer network to benefit from Aquamarine? You do not. You can, but you do not. And now we also need to consider what's a network. A network is obviously an amalgamation of peers. So for you to run a network, it would be multiple peers, and it probably would be permissioned as opposed to permissionless. You can do this, obviously, but Aquamarine is really empowering you to participate in safely participate in permissionless peer-to-peer networks, where you get the power and the fault tolerance of other peers out there contributing. And so no, you don't have to run one, but you may want to run your own node, but you don't have to run a network at all. As it stands right now, we're even providing a test net for the development purposes, and so you don't even have to run a node. You can just deploy your services or use services that are hosted on a very accessible test network. And we are thinking of, depending on the uptake, of a production hosting of a production network that we basically provide, and developers can either join with their nodes or just utilize. That was another great question. And oh yeah, and I said somewhere along in the talk, I said monetization. We want to empower developers to monetize their work. And one of the things we're doing, we're in the process of developing a blockchain-based licensing system for open source software, peer-to-peer software, and trying to shift the value capture from the big cloud operators, who currently basically capture all the value, pretty much, particularly on open source contributions, to open source developers. So what you can do then, or what you will be able to do in the not so distant future, is you develop a service, and in addition to the software license, you attach to it a service license, and that service license is immutably backed up on, or immediately it's contractually and immutably deployed on a blockchain. I think it's going to be Ethereum-like-ish, and that allows you not only to control the use of your service if you care, but you actually can start implementing monetization patterns and start making money. And one of the things where we believe peer-to-peer is, because of the reusability of services, actually even small services that are crucial to a lot of other services, actually sort of in a pyramid development, actually can monetize much better than in any other environment, if that is something you are interested in. So now okay, so all right, so this, okay. Yes and no. So the question, Shubham, is I hope I'm pronouncing your name correctly. How do we maintain latency SLAs? SLAs is interesting, and I think within a peer-to-peer environment, fundamentally, you have to rethink your SLAs a little bit. Part of it is just that, as I said, in a peer-to-peer environment, you expect peers to drop, to shift, to move, to evolve, rather than treating it as an exception. And that impacts how SLAs are offered. Now, at the service provider, you can't provide SLAs at just as you want with any cloud, big time cloud provider you get today. You can do it, and just like with say Amazon SLAs, for example, it's the failure and it's the failure at the execution time that starts adding to your minutes of unavailability and your failure of executing your SLA. But that's not, so just to make clear, this is not necessarily a network issue, it's a service provider issue. So if you, Shubham, want to give 5 nines on your service, then you are totally happy or eligible to do so. If I was you and I was doing this, I would very, very much probably run my own nodes, right? I mean, you should be able to monetize. If you're giving 5 nines, you should be able to monetize. And if you're able to monetize, then you probably want to run your own nodes in order to eliminate any failure, or at least control your failure possibilities and probabilities. Did that answer your question? So, okay, I wouldn't necessarily call it a private network. One of the things, and Alexei actually asked me to to put it in the presentation, and I didn't want to because I thought it might confuse things a little bit. One of the things you're doing when you're building your Airscript, you're basically building a sort of a temporal virtual private network, right? Because the realm, your topology of the execution path is really limited to what you're specifying programmatically within your Airscript. So you don't need to run a private network. You can host other people's services as well, right? I mean, it's not an isomorphic relation, not a one-to-one relationship between a service and a network. A node can run as many services as it has capacity for. So you can still operate in a permissionless public network, but provide performance guarantees around your specific nodes. It's almost like the inverse of staking nodes, right? Well, it's not the inverse, but it's like staking nodes. I mean, you run your own staking nodes in a blockchain environment, and you're still part of the public system, but it's your nodes. You guarantee their availability, and unlike an asset, and the SLA equivalent is basically if your staking nodes don't perform or run when it's supposed to run, you get slashed. And basically, you can look at it the same way. You run your nodes in a public network, and your services, just by the way the SLA is structured, and developers seek out those services, you basically create a virtual private network within a permissionless public network. Does it make sense? Okay, cool. So yeah, I obviously, as you can see, like I'm very like, I'm not a big fan of private in the sense that you have to run your network, because this is almost like defeating the purpose of having peer-to-peer, right? Because if you run your private, you're centralized. If you're centralized, you probably could just run it on a cloud, on a basic cloud setup. But the whole point is that the accessibility of in a permissionless network, the discovery and the use of your services is just so much more than anywhere else. And you get this organic marketplace for discovery of services and the reuse for them. Anybody else? All right, that's all I got, folks. thank you very, very much for having
Yep.
me, and thank you for being here. I apologize for the snafu with the slides. I'll make them available as a PDF. I'll send them out, and you all have a great great evening, great weekend. Stay safe, and thank you very much.
Thanks, Bernard. Thanks, Anna and Alexei. Thanks for asking the questions. Interesting presentation, and thank you for everyone else attending. And I guess have a good day and a good evening.
Thank you, everyone. Bye.
All right, bye, everybody.